Hi everyone, welcome to CS 188 Section 5, and today we'll be talking about MDPs and starting on reinforcement learning. Alright, so we did MDPs briefly last time, so first I'll do a recap of how they're formulated, but now we'll actually talk about how to solve MDPs to get a good policy. Okay, so the formulation is that we have a bunch of states and actions. We also have a transition probability, T of S, A, S prime. This can also be viewed as a conditional probability of the state S prime given state S, A. And we also have a reward. Given that we are in state S, we take action A and we end up in S prime. And we also have a discount, gamma, which tells us how much we care about current rewards versus future rewards. And in all of these, let's keep the example of grid world in our mind. So here we have our grid, and some states are good. They give you a high reward when you go to them, and some are bad. And the goal is to maximize your expected reward. So what's our goal? It's to find the policy pi that maximizes the expected sum of discounted rewards. So if we read this, we have our reward R, we have gamma, which is our discount, so it's between 0 and 1. And we sum over all time, and we need to take an expectation with respect to our policy pi because we have probabilities. Our transition right here, T of S, A, S prime, when we take an action, we're not sure where we go. So we need to do the expectation, the average. So what quantities do we care about? So we're going to talk about basically three quantities. One is our value V of S. So given a state S, how good is it? And this will just be a real number. We also have the notion of a Q value, Q of S, A, which is similar to the value, except Q value is how good is a state and then taking an action from that state. So this is also a real number. And finally, we have our policy pi of S. So given the state S, the policy pi will produce an action. So output an action A. So now when we're talking about MDPs, we have a set of equations that we always refer to, and we call these the Bellman equations. And it's basically just an alternating recursion. So first, let me write it out. So we have the value S equals the max action of the Q value from that state over the actions. And now I'll write down what the Q value is. So Q is the sum over all possible next states, the probability of going to that state, times the reward of that transition, plus the possible future reward, which is the future value. Okay, so now that we have these two equations, let's look at the recursion. So Q of S, A tells us how good a state in an action is. So the value is simply the action that returns the highest Q value. And then the Q value is considering all possible next states, S prime given S, A, the likelihood of that transition, and then how good it is the current reward. So this is current, plus the discounted future reward, which is the value. Okay, so now that we have this set up, let's talk about all the different ways of solving and getting our policy pi. So first, let me write down all of them, and then we can talk about them. So first, let's just group these into three different categories. So we have 1, 2, and 3. Okay, so first let's talk about value iteration. So what value iteration does is it starts off with all the values initialized to 0, and then it iteratively goes through, and for iteration, should be a k there, at vk plus 1, we update the value to be the maximum action over the sum of considering all next states s prime, the probability of doing that tuple s prime, the reward s prime, plus the discounted value of the current next state. So when you look at this in the grid world, as you've seen in lecture, the values propagate out. So for example, if I have grid world right here, and I have plus 100, on the first iteration, everything's 0, then this will become non-zero, then everything 1 away will become non-zero, then everything 2 away will become non-zero, then 3 away, and then 4 away. And this is what this equation is doing. Then you have Q-value iteration, which is pretty much the exact same thing, except if you go back to your Bellman equations, you replace the V's with Q's. So as you can see, it's the exact same, except the max has gone away, since the Q-values already has an action, it's S comma A. And then the value of the next state is the max over the Q values, the current estimate. Then we have policy extraction, which is given either V or Q. How do we get the policy? So for values, if we want to extract the policy, it's the best action, and then we consider the expectation with respect to the next state. So sum over all S prime, the probability, times the current reward, plus the discounted reward of value of the next state. Now, policy extraction from Q values is much easier. The Q values for a fixed state, you just take the action that gives you the highest Q value. So argmax over A. Now we have policy iteration. So if we look at policy iteration, it's 2 phases. First, we have an evaluation phase where given our policy pi I, which is written all over, you basically take actions according to pi I. So the value is the sum over possible next states, the transition when you act according to pi I, the reward when you act according to pi I, plus gamma times the discounted future value, or value of the next state. Then, once you run this to convergence, you then improve your policy. So how do you do that? Well, it's basically going to be very similar to the extraction part. So argmax over actions, consider all next states S prime, the probability of that tuple S comma A comma S prime, the reward of that tuple, plus gamma times the value of the state you end up in. So now we can kind of look and compare all of these. So first, let's look at policy iteration versus value iteration. So as you can see, the equations are very similar, except value iteration has this max over A, while policy iteration, the valuation does not. So this is because policy iteration uses the current estimate of the policy to get the value, while value iteration just takes the best one, the max over all A. So the evaluation phase in policy iteration, this will run faster because there's no max. Everything in here is a linear equation, and this can be solved very quickly. While in value iteration, this max creates it slows things down computationally. However, the trade-off is that we need to somehow improve our policy. So there's a stage in policy iteration where we need to do improvement. So I suggest whenever you need to do problems with regards to MDPs, you have something like this cheat sheet out, which has all your equations, and they're all just variations on the Bellman equations, which I wrote earlier. Okay, so now we're going to move on to reinforcement learning. So in reinforcement learning, there's an agent. The agent takes actions. Then the environment responds with the next state of the agent and also a reward. And this is reinforcement learning in a nutshell. So what the agent wants to do is the agent wants to take actions that the environment will give them large rewards for. And this loop goes on and on forever. So you can view this as kind of like life. Maybe you can view the agent as yourself. You're taking actions and you're hoping to get rewards from it. Maybe it's getting a good grade in this class. That might be a long-term reward. You can also eat the marshmallow. That's immediate. Okay, so this is very similar to MDPs, except there's a key difference. We don't know the transition probability, t of s comma a comma s prime, and we don't know the reward, s comma a comma s prime. So when we take an action and the reward that we get from it, basically the environment is a black box. We do something, it spits something out. We don't actually know how it works. Before in MDPs, we knew how it worked. We knew T and we knew R, and that defined our world. Now we don't. So this makes things tougher. What does this mean? Well, because it's a black box, it means we have to interact. We have to take actions in order to figure out what's good and what's bad. So the approaches that we're going to talk about in reinforcement learning for maximizing our expected reward and getting a good policy are basically going to be sampled versions of how we solve MDPs. So let's talk about them right now. So the first one is called temporal difference learning. We'll call this TD learning. So how does it work? First, we get a sample from the environment. We take an action and we see what happens. So it's the reward from the current state, the action that we decide to take, and where we happen to end up, plus the discounted value of where we happen to end up. So we acted in the world and we found out this information. Now we can update our estimate of the value. So our new value is going to be 1 minus alpha. I'll talk about alpha in a second. Of the current estimate plus alpha times what we just saw. And alpha is going to be between 0 and 1, just like gamma. So what this does is it says our new value over here is some fraction of the old value plus some fraction of the new value. So basically this is kind of an averaging effect. So we take actions in the world, we get samples, and we update our value v pi. So you can see this is very similar to MDPs, in which we are updating our values iteratively. Now there's also the same thing for Q values, and this is called Q learning. So this is going to be very similar. So we get a sample from the environment by having the agent take an action. We get a reward, s comma a comma s prime, plus the discounted value of where we end up. But we have Q values. So it has to be the max over Q values of s prime comma a prime. Then we do the same exact thing. We take our Q values and we need to update them. So it's going to be some fraction of the old Q value plus some fraction of our new Q value, which we had a sample of. So by running temporal difference learning or Q learning, And interacting in the environment, we can get estimates for either our value function or our Q values. And in the solutions, which I'll do next, we'll see how to actually run these algorithms.